Welcome back to the Smart Reactors podcast. In today's episode, we will be discussing the key differences between hydrophilic and hemocompatible coatings and what they mean in today's medical device coating technology industry. I'm joined today by the CTO of Smart Reactors, Mark Brassil. Thanks so much for joining us again, Mark. It's great to have you back. So I suppose to kick off today's podcast, could you tell us the difference between hemocompatible and hydrophilic coatings?
I can, yeah, and it sounds like a simple question, but it isn't, because usually when people say hydrophilic, they mean a lubricious coating. Okay. So that's a coating to reduce friction, and not every coating that reduces friction is hydrophilic, meaning water-loving. You have your PTFE coatings, so they're lubricious, but they're not hydrophilic. So these terms get very confusing. Likewise with hemocompatible coatings, every coating that goes into the body will have been tested for hemocompatibility. So really what people mean is coatings that have a really high level of hemocompatibility performance. Your heparins, our own coatings that are specifically designed to reduce the risk from thrombus. So that, I know that's a complicated answer to what sounds like a simple question, but really it breaks down into coatings that are designed to reduce friction and coatings that are designed to reduce blood clotting.
Okay, I see. And why is it important for, let's say, medical device manufacturers and clinicians to understand the difference between these two types of coatings?
Well, the manufacturers need to understand their application. What are they trying to achieve with a coating? So if you have a catheter, you want to track it through tortuous anatomy, you need a lubricious coating, either hydrophilic or otherwise. Whereas if your device risk is from thrombus formation, then you need a coating that's hemocompatible. So it's about your use case and the risks of your device.
Okay, and as you mentioned there, lubricious and hemocompatible coatings have different medical device applications. Could you give us maybe examples of what devices are suited towards each coating?
Sure. Your hemocompatible coatings tend to go on things like stents, on vena cava filters, or bypass grafts, and any large surface area devices like dialysis or ECMO perfusion. Those type of devices tend to be where hemocompatible coatings live, whereas things like catheters and intraocular lenses, they will get a more lubricious coating to reduce wear or to reduce contact and the force from contact.
I see. And is there any particular type of medical device that may require the two types of coating, lubricious and hemocompatible?
I'm not aware of one that specifically has to do both. Usually you'd want a hydrogel or a lubricious type coating where it's to reduce wear. They don't tend to be the areas where you have your issues around hemocompatibility or thrombus formation. So they're two different applications, really.
Okay. And how do the manufacturing processes, let's say, differ then between lubricious and hemocompatible coatings?
Yeah, there's lots of different chemistries available for each. So if you take the hemocompatible coatings, some of these will need kind of an advanced surface prep for your heparin type coatings. The hemocompatible coatings tend to be at least an order of magnitude thinner than the hydrophilics or the lubricious hydrogel type coatings. The hydrogel type coatings are usually applied with a solvent process, a dip process, and they're then cross-linked using ultraviolet energy or thermal energy. The hemocompatible coatings may have a chemical type cross-linker, or they may use thermal cross-linkers, so they tend to have very different chemistries.
Okay, and is there any type of testing or validation that is typically required before these coatings make it into, I suppose, clinical use?
Loads,
yeah.
Loads, and it does, and they're different. So the testing you need for a hemocompatible coating is going to be different than the testing you need for a lubricious coating. With your lubricious coatings, it's usually pretty easy to tell if they're there. That's not always the case for hemocompatible coatings. Your risk from lubricious coatings tends to be kind of increased surface friction or particulate, whereas from hemocompatible coatings, your risk is kind of thrombus and sometimes allergies to the material. So it really depends on your application. There isn't one defined set of testing that you need to do for everything. So you need to understand your coating, you need to understand your device, and you need to understand the latest requirements from the FDA and from the regulators. Okay,
I see. And in terms of hemocompatible coatings, then as you said, they help to reduce blood clots. Do they reduce blood clots straight away, or do they take time after the device is implanted?
Instantly. It has to happen instantly. I mean, your progression towards clot starts in less than the first second from when your device contacts blood. So it's something that has to start immediately.
Okay. And once hemocompatible coatings are applied to a particular type of device, how do medical device manufacturers, let's say, ensure that they perform with long-term stability?
Yeah, it's a series of different experiments. There isn't one test fits all for everything, so you got to ensure your coating coverage is there, that you have a method for detecting it. In the case of heparin, you have to kind of quantify the amount of heparin that's there and the surface activity. You've got to look at your durability in simulated flow, simulated use to make sure the coating doesn't come off. And your ultimate kind of preclinical evaluation of long-term performance is going to be in an animal model appropriate for your device.
Okay. And from your experience, what are the most common ways that these types of coatings could fail, and is there any way we can prevent them?
Sometimes it's hard to distinguish a coating failure from a device failure. So if you talk about devices that fail, for a lubricious coating, you can often tell. You can see this in the literature. You will see full coating removal. You can see that even on gloves or on auxiliary devices. You'll know that it's come off. That's happened with lubricious coatings, and it's happened with PTFE. So manufacturers have good process controls for that. With hemocompatible coatings or with the risk of thrombus, it can be harder to actually detect a failure because you can have thrombus buildup that's not related to the surface. It's related to hemodynamics. It's related to your patient's baseline coagulation and reactivity. So you have to look at where can this failure occur, what are the clinical manifestations of that, and how can you detect that as soon as possible.
Okay. And over time, will these types of coatings degrade in the body?
Usually not. No, usually the kind of coatings that are used, they're covalently cross-linked in a matrix of some form. They don't tend to break down readily within the body.
Okay. And in terms of regulatory requirements, would you say typically that lubricious or hemocompatible coatings are stricter?
Devices that have hemocompatible coatings tend to be more your implant type devices, your class 3 devices, your higher risk devices, so they have more of a regulatory burden. If you use heparin as your hemocompatible coating, then you increase the regulatory burden on testing, even what would otherwise be lower risk devices. Your lubricious coatings tend to be on devices that are less high risk anyway. They're catheters, they're used kind of for a short period of time, then they're disposed. So again, complicated answer to what sounds like a simple question.
Absolutely,
Gillian.
I can imagine. And I suppose, how does the choice of a particular type of coating maybe affect the timeline between R&D, then into testing, then maybe into clinical use?
Yeah, you've got to understand the complexity of applying that coating. How well established is that the process for applying the coating, because it can take a lot of time to develop that. If you're using something like a drug like heparin, that's going to add time in terms of the regulatory testing you have to do, your shelf life, stability testing, and you may have a different notified body for a drug versus for a device only. So you have to understand all the complexity that any coating choice brings to your device development.
Thank you so much for joining us, Mark. It was a pleasure to have you on the podcast again. That wraps up today's episode of Smart Reactors. You can join us next week where we dive into Smart Reactors' camouflage coating technology and how it can enhance the performance of implantable devices. So stay tuned.